Scala is a functional and object-oriented programming language built on the JVM. Scala Native takes this language, loved by many, and brings it to bare metal. Scala Native is an optimizing, ahead-of-time compiler and lightweight managed runtime designed specifically for Scala. Dennis Shabalin is a research assistant at the EPFL and the primary creator of Scala Native. In this episode, Adam Bell interviews Dennis about the motivations behind the Scala Native project, how it was implemented, and future directions. He also briefly touches on how Scala Native made cold compilation times of Scala code twice as fast. If you're interested in functional programming, compiler design, or you want to learn some interesting tidbits about garbage collector design and trade-offs, then you will like this episode. In past shows, we have covered many of the newer programming languages and the new twists on old programming languages. We've talked about Scala.js, which is related to this episode. We've talked about Swift on the server. We've also talked about Rust at Mozilla. If you want to find these episodes and many others, download the Software Engineering Daily app for iOS or Android to hear all of our old episodes. They're easily organized by the categories, and as you listen, the Software Engineering Daily app gets smarter, and it's going to recommend you content based on the episodes that you're hearing. If you don't like an episode, you can easily find something else because our recommendation system knows what you like. These mobile apps are open sourced at github.com/softwareengineeringdaily. If you're looking for an open source project to hack on, we would love to get your help. We're building a new way to consume software engineering content. We've got the Android app, the iOS app, recommendation system, the web front end. There's going to be more projects coming soon, and if you have ideas for how software engineering media content should be consumed, or if you're interested in contributing code or just hanging out in the Slack channel and seeing what transpires, come to github.com/softwareengineeringdaily or join our Slack channel. There's a link on softwareengineeringdaily.com. You can send me an email, jeff@softwareengineeringdaily.com. I'd always love to hear from you. And let's get on with this episode. Who do you use for log management? I want to tell you about Scalar, the first purpose-built log management tool on the market. Most tools on the market utilize text indexing search, and this is great for indexing a book, for example. But if you want to search logs at scale, fast, it breaks down. Scalar built their own database from scratch, and the system is fast. Most of the searches take less than a second. In fact, 99% of the queries execute in less than a second. That's why companies like OkCupid and Giphy and Career Builder use Scalar to build their log management systems. You can try it today, free, for 90 days if you go to the promo URL, which is softwareengineeringdaily.com/scalar, SCALYR. That's softwareengineeringdaily.com/scalar. Scalar was built by one of the founders of Writely, which is the company that became Google Docs. And if you know anything about Google Docs history, it was quite transformational when the product came out. This was a consumer-grade UI product that solved many distributed systems problems and had great scalability, which is why it turned into Google Docs. And so the founder of Writely is now turning his focus to log management. And it has the consumer-grade UI. It has the scalability that you would expect from somebody who built Google Docs. And you can use Scalar to monitor key metrics. You can use it to trigger alerts. It's got integration with PagerDuty. And it's really easy to use. It's really lightning fast. And you can get a free 90-day trial by signing up at softwareengineeringdaily.com/SCALYR. softwareengineeringdaily.com/scalar. And I really recommend trying it out. I've heard from multiple companies on the show that they use Scalar, and it's been a real differentiator for them. So check out Scalar, and thanks to Scalar for being a new sponsor of Software Engineering Daily.
Dennis Shabalin is a research assistant at the EPFL and the primary creator of Scala Native. Dennis, welcome to Software Engineering Daily.
Hey.
Scala is a language built on the JVM. Could you give a brief overview of Scala the language before we get into Scala Native?
So Scala is this pretty cool language originally designed for JVM. It really can be described as a mix of functional and object-oriented programming. It really doesn't bias toward one or another style. It really tries to blend both together because there is both good and bad on both ends. Like, for example, functional programming is basically considered like the better type of Scala we have, and object-oriented to be more of a Java style, old-schooly, less popular side, but still language doesn't bias towards one side or another. You can perfectly do object-oriented, classical object-oriented programming and fancy functional programming at the same time, which is pretty unique because most languages are heavily on one side or another, which is often considered to be like a negative side of Scala because it's very unopinionated. But anyway, that's what it is.
Yeah, it makes sense. So Scala lets you you can combine sort of a Java style OO with a ML or Haskell style functional composition.
Absolutely, yeah, that's it.
What is Scala Native?
So Scala traditionally has been a JVM-centric language. So it used to compile only to JVM bytecode as the only target. And what it means is that it's really plug and play on JVM. You just compile your Scala courses to bytecode, and then you can run it alongside your Java application. That was the original backend, the original platform for Scala, but since then we got way more things. The first major experiment to do Scala outside JVM was .NET backend. That didn't work so well because of the differences between how JVM and common language runtime handle generics, so it was a bit difficult. I think the first successful alternative platform for Scala is Scala.js by Sebastian Doran. So basically, it's really a major difference in terms of how you run your Scala apps because you compile them to JavaScript through this very elaborate advanced toolchain they have. And Scala Native is very much a similar project to Scala.js, but instead of compiling to JavaScript, it compiles to native code. And when I say native code, I mean more like C++ standalone binaries that completely just don't require any virtual machine to run it. So you get x86 or ARM binaries that you can just copy paste into any machine with the same architecture and just run it. Of course, it has good and bad of native style development, but it's really kind of the core idea of the project is very simple, is to compile Scala to native binaries.
Makes sense. So, Scala.js gives you the ability to run in the browser. What problem does being able to run as a native application solve?
So one of the issues with JVM, as I see it, is that JVM is a really heavy machinery. So it really requires quite a bit of footprint just to run the VM. So you can see it in terms of memory used. You can see it in terms of application startup time. You can see it sometimes in terms of overhead of the whole services, like just compilation behind the scenes. And it's really because JVM is very, very advanced, multi-stage, multi-tier VM, and it's really hard to support all this functionality without incurring some overhead. So what Scala Native, the way Scala Native is different, is that we do most of the expensive parts like compilation ahead of time. So it means you already have a pre-compiled and pre-optimized binary. So when you start it, it just runs your app. It doesn't do the whole multi-tier VM thing. So we don't have interpreter. We don't have multiple tiers of compilation. And we just, whenever we emit a binary, that's it. There is no recompilation at runtime. There is no tricks with it. It's a simple binary, which means we have way lower footprint, and both in terms of memory and in terms of startup time. This can be useful for a number of use cases of applications, like, for example, command line tools. So for command line, it's extremely important to start up quick, do your job, and then die. This is an area where JVM is really bad at right now because just starting the VM is extremely expensive operation. So you definitely see this kind of like initial slowdown if your app is not long running.
So that is what people refer to as like the JVM warmup. Is that right?
Yeah, exactly. So it's like JIT warmup. And it also has to do with the fact that when you run code in JVM, it actually goes through a number of stages. So first you go through interpreter. Interpreter is really slow. It is not meant to be there for a long time, so it tries to go to compiled mode as soon as possible. And there are at least 2 compilers right now which are used in production JVM, C1 and C2. C1 emits simple code to avoid the interpretation cost. And C2 does a very advanced optimizer that only optimizes heavily used parts. So basically, you have a very elaborate machinery, which means that you don't get to optimize code only until your application is warmed up. In native, we have basically equivalent assumption in between C1 and C2. So we already heavily pre-optimize your code before you run it. But at the same time, it's not quite the same as a VM, so it draws some pros and cons.
Yeah, so if you have a long-running Java app or a Scala app, I guess, then the costs of this warm-up maybe doesn't matter so much. But if something has to start up frequently, then re-optimizing it is a lot of overhead.
Absolutely, yeah, that's it. And another area, apart from command line tools, is different types of user-facing apps where you can observe and perceive the startup time, which often are simple graphical apps. Like, for example, start an Eclipse takes minutes. I don't know. It's just before it's and you never close it, right? Because you're afraid to close it, because once you close Eclipse, you'll have to go through the same thing again. It's basically not Eclipse problem as far as I can tell. It's largely a JVM problem because, for example, other IDEs start much faster than Eclipse.
Yeah, I use IntelliJ, but I found the same thing. Yeah, I try to keep it running. In your talk, Scala Goes Native, you were describing the JVM as a golden cage. Is this sort of what you mean by that, or could you describe this concept?
So this metaphor was basically try to motivate why we don't try to artificially limit what you can do in Scala Native like JVM does. In particular, we don't try to sandbox your code so that you can only write a very safe code which never escapes the cage, basically. That's what I meant by the cage, is that we let you use low-level, system-level tools like raw access to memory, raw pointers, and stuff like that, which is potentially unsafe, but it's actually necessary in some domains like systems programming where you want to have a very low-level control of your memory. The benefit is that you get more control as a developer. You're not limited by the language and the VM, because you can do whatever you can do in C and C++. On the other hand, you do lose some of the safety you get on JVM, but this is kind of a trade-off we take.
That makes sense. So is this strictly for memory management, or how about Interup?
So generally, Interup is basically... So Scala Native exposes a number of language extensions aimed primarily at Interup with C code. And in a way, it's a bit like writing C code in Scala. So we expose things like pointers and structs. So you can do familiar C-style programming, but it also means it's extremely easy to call C code. You don't need to go through a number of layers of bindings to get there. You can just do it all in Scala without any C and C++ code in the middle. But it also means that if you can call arbitrarily C code, you also can get arbitrarily issues that C code has. Like, for example, different types of safety issues around buffer overflows and so on and so forth. So it's definitely a trade-off. It's not free, like calling C code is not free in terms of like safety guarantees you get. But again, this is the kind of trade-off we make. We don't try to be as safe as possible. We try to be as flexible as possible.
Makes sense. You want to give people that tool even if they, it could go wrong. So how about memory management on the JVM?
So JVM is basically GC-only platform. There are some very well-hidden but extremely well-known areas like Sunmisk and Safe, which lets you do unmanaged memory and manage it yourself. Like, for example, you can allocate unmanaged memories to Sunmisk and Safe and then do raw memory accesses on it. It's basically as unsafe as pointers in C, only JVM people try to hide it from you, even though every major performance-centric framework actually uses it. Like, for example, Spark does off-heap memory to manage most of its data because it's just too expensive to allocate everything on GC heap. But JVM people like you to believe that you only have GC, which is the main paradigm. And it's actually like GC on JVM is really good. So very often it's a good idea just use that and not do any unsafe memory management. In Scala Native, we say both coexist, and you have APIs for both, and they're both easy to use. So definitely unmanaged memory is a dangerous thing. You can definitely shoot yourself. But for example, if you want to do some domain specific thing to optimize your memory layout and so on and so forth, you can do that without jumping through the hoops like on JVM.
Makes sense. So, the JVM it purports to be memory managed, but if you look at these high performance apps, they're using backdoors to sort of actually do manual memory management. Yeah,
and it's like most of them really go far away to try to sidestep the cache to find this small doors outside to get more freedom, but it's on JVM it's really hard to do those kind of things.
That's where the cage metaphor comes in.
Yeah.
Okay, so now that we understand some of the motivations for getting Scala to run natively, not on the JVM, maybe let's discuss some of the implementation. So could you describe the compilation steps that it takes to get from Scala source to a native application?
Oh, sure. So it's actually a bit involved, and there is a good reason we have every single step on the line, but it's actually a really multi-step process. So first thing you do when you go from a Scala source, so you always start with Scala sources, which is a source of truth. And in case of Scala Native, you end up with native binary. But it's not the one-step thing like from Scala source to native binary. The first thing you do is you do parse and type check, and basically you do the pipeline from the main Scala compiler from JVM. And this contains a number of things, but the most important one, I guess, is type checking, because type checking in Scala is very involved. We don't re-implement type checking or the language. We keep the same core, the same language as Scala and JVM. And then later, once Scala compiler is almost done, we branch off and we emit something called NIR. NIR is short for native IR, which is our own intermediate representation. So this NIR is the format we work with in our toolchain. And when I say our toolchain, I mean linker, optimizer, and cogen. They all speak this language as if it was like a real language. So to get from NIR to binaries, now we have one step closer, because NIR is already quite more low level than Scala. So for example, many things are gone, like there are no nested classes, there are no generics. Type system is much more simpler, and it's actually very close to Java bytecode rather than Scala language. And the main difference from Java bytecode is that it's an SSA form, which makes it very easy to emit LLVM later. SSA is a form for code representation, which is very nice for optimizing compilers. So from NIR, we need to get native binary, and three major steps on this way is first linking. So linking loads a minimal subset of your class path to satisfy your application requirements. Like for example, an app that doesn't use regular expressions should not precompile regular expressions in the binary, and so on and so forth. So we try to really limit an amount of code we put in the final binary, not to include every single class on the class path, because sometimes class passes get quite bloated even though you don't use some of the things. Sometimes people depend on a library even though they use a single function from it. So we do something called whole program code elimination at link time. And then after that step, you get a minimal subset of the class path, which we optimize through our own optimizer, which removes common patterns which LLVM doesn't know how to optimize well. And then in the end, we emit LLVM IR, which is another IR, but now for LLVM. LLVM is this project for reusable compilers, basically. So it's a core for CLine compiler, and it's also used by many, many other open source languages. And it's actually very well documented and very nice to work with. And from there on, it's basically LLVM's jobs to get from LLVM IR to native code, which we typically don't touch that much.
The octopus, a sea creature known for its intelligence and flexibility. Octopus Deploy, a friendly deployment automation tool for deploying applications like .NET apps, Java apps, and more. Ask any developer, and they'll tell you that it's never fun pushing code at 5 p.m. on a Friday and then crossing your fingers, hoping for the best. We've all been there. We've all done that. And that's where Octopus Deploy comes into the picture. Octopus Deploy is a friendly deployment automation tool, taking over where your build or CI server ends. Use Octopus to promote releases on-prem or to the cloud. Octopus integrates with your existing build pipeline, TFS and VSTS, Bamboo, TeamCity, and Jenkins. It integrates with AWS, Azure, and on-prem environments. You can reliably and repeatedly deploy your .NET and Java apps and more. If you can package it, Octopus can deploy it. It's quick and easy to install, and you can just go to octopus.com to trial Octopus free for 45 days. That's octopus.com, octopus.com.
Yeah, so if I understand this, you have your Scala code, you're using the front end Scala compiler to get some intermediate representation, and then doing some transformations and then passing that through to LLVM. Is that the big picture?
That's pretty much the gist of it.
And then because there could be a lot in your class path, you're making sure that you only include things in that binary that are actually called within the program.
We don't know if they're going to be called, but we try to analyze it and kind of do our best guess on what's going to be called, yeah.
Okay, yeah, makes sense. So one of your frustrations with the JVM was that its garbage collector doesn't fit every use case. So many listeners may know that there are different types of garbage collection strategies. I was wondering if you could describe a couple strategies for performing garbage collection.
So on JVM, we actually have a number of built-in garbage collector. As far as I understand, in Java 9, the default one is called G1. And G1 is the latest collector from Oracle, which is optimized for latency-centric workflows. So typically, GCs are often kind of put in either latency-sensitive or throughput-sensitive buckets. So what latency-sensitive means is that the GC is optimized for shortest pause that the GC can take to collect garbage. But these pauses can be extremely frequent, but every single pause is small. And throughput-centric collectors care about not the length of a single pause, but rather the total sum of time spent in GC. So for example, throughput-centric collector can take less pauses, but makes them much longer. And basically on JVM right now, the official ones is G1 for latency sensitive and parallel GC for throughput sensitive workflows, as far as I understand. And CMS, which was previously the default, is deprecated as of Java 9, which is a bit sad because on some of our workloads like Scala Compiler, I think CMS is still the best one, but otherwise it's basically three main collectors we have right now, with CMS being deprecated. The general themes for all of those collectors is that they're typically generational, they're typically at least parallel, often concurrent. So what concurrent means is that collector runs alongside your application and tries not to stop your application as much as possible. So that basically it does garbage collection, not just in parallel, as in doing multiple threads of garbage collection, but also concurrently to your application. So compared to all of this, so where does Scala Native stand? Right now we have a rather simple garbage collector called Imix. It's inspired by a paper. You can see more information on our website if you're interested, but the general idea is it's a single generation collector, which is right now optimized for predictability. It's not concurrent today. It's stop the world. And we currently optimize mostly for throughput, and latency sensitive is our next big milestone, which we haven't reached yet.
Okay, that makes sense. You also have, as I understand it, you have more than one GC available in Scala Native.
Yeah.
Maybe you could describe what they are?
Right now, the default one is actually not Imix, it's called Boem. So BoemGC is this super easy to use plug-and-play garbage collector, which was designed originally for C and C++. And the reason why it's even possible at all to make it work in this environment is that garbage collection is conservative. So what does it mean? It means that garbage collector doesn't really require your app to declare ahead of time kind of the layout of all objects. It will conservatively guess what objects are based on their size and layout. So for example, if a field at some specific offset looks like a pointer, it can consider the pointer even if it's not, as long as it satisfies a bunch of properties that GC wants to see from pointers. This is more expensive than precise garbage collection. So precise garbage collection knows exactly at which offsets you have pointers and at which offsets it's just data. So it needs to do less work. The main reason why our current new collector called MX is faster is because it's precise. So we do use information about the whole object layout, and it's way easier to collect the garbage. It's still conservative in one small aspect, but it typically doesn't matter much. It's the stacks are conservative, but it typically is not a problem. Another cool thing about MX compared to Boem is that it actually uses a very smart data structure for allocation and collection, which lets it bump allocate most of the time, which is really important because bump allocation is the fastest way to allocate, and Boem still uses a free list from time to time, and free lists are typically quite expensive in our own experience. And apart from this two, we have another collector called NoGC, or settings called native GC : none. So that one lets you completely disable the garbage collector. And the idea behind that one is to kind of have a rough understanding of how much time is spent in garbage collection and what's the baseline performance, what's basically the perfect garbage collector. Because essentially, allocating and never freeing is actually extremely close to perfect garbage collection. It's not perfect because it will still allocate objects far apart if objects were not allocated at the same time. So it can still cause problems with memory locality, but most of the time it basically spends zero time in garbage collection, so it means it's as low overhead most of the time for most applications. And we use it as baseline to benchmark our GCs. So it's basically main purpose is benchmarking. And apart from that, there are some use cases like extremely short-lived applications which really don't need to manage memory because they like run for less than a second and they don't allocate gigabytes of memory, but maybe hundreds. So for those kind of apps, it's actually beneficial to be able to disable garbage collector because it means they will run at best performance possible.
Makes sense. So none exists as sort of for performance testing, but in actual fact, it can be used for like a command line app. So you have none, so you can test what you're calling like a perfect GC against the two that you have. When you do this type of testing, like how do they perform compared to a perfect standard?
So compared to our reference, so typically MX is somewhere around 20% overhead. So this means if you add MX, your app will run 20% slower. In comparison to Boem, Boem is somewhere around 100%. So basically enabling GC slows down your application by a factor of 2x, which is pretty bad. And it mostly has to do with the conservative nature of the collector. So MX is at 20%. It's actually still higher than we want it to be. I think we can get it to 10 or maybe even less without changing the design of the collector too much.
Interesting. Do you happen to know, like 20% away from absolutely perfect doesn't sound too bad.
Yeah.
Do you know like where the JVM's generational garbage collector would fit on such a measure?
It's a bit hard to compare with something like CMS or G1 because they run concurrently. So it's typically under 5%, and I would probably say probably even less than that, because for concurrent garbage collector, you never perform the garbage collection on the actual application thread. You have a separate thread which only pauses application to do simple things like scan the stack or wait for this condition to hold. So it's typically short pauses of 5 milliseconds or less. They can be frequent, but typically as far as I understand, it's like under 5%. So basically this is our like goal performance is to be on par with JVM. Right now, we don't guarantee parity with JVM in terms of performance. So there's still quite a bit of work to be done there.
Makes sense. So, some people's complaint with the JVM is sort of the stop the world garbage collection, but you shouldn't go to Scala Native to get away from that because that's all you have at this point.
Yeah. So at the moment, we don't solve the stop the world problem. So we're researching ways to refine our GC further, but right now, like as of released version, only no GC has no stop the world problems because it doesn't GC.
Yeah, makes sense. So now I think I understand how the GC works. I'd like to look a little bit at Scala Native usage. So is Scala Native the same language? Is it Scala or is it something like a superset?
So Scala Native at its core is one-to-one Scala. So there are very few differences in terms of how we treat normal Scala language features. And they mostly are around edge cases, like what happens when you call a method on a null, or what happens when you do a cast, which doesn't make sense. So on JVM, those cases are defined to throw exceptions. Some of those are just undefined behavior on native, so it means anything can happen if you do this. Typically, it means it just crashes with a seg fault, which is basically a bit worse in JVM, but still it's easily debuggable through native tools like that will show you a stack trace and will effectively show you as much as a null pointer exception. We don't currently guarantee one-to-one parity in the edge cases, and it's likely we will never have this because it's typically been a non-issue for us. It's a bit more annoying to debug some of this, but essentially it simplifies our implementation quite a bit. And apart from the core language, which is almost exactly the same, like 99% the same, we have a bunch of extensions for Interup. So Interup extensions are very different from Scala and JVM. They don't have anything similar. We do have row unmanaged pointers and things that go with them, like memory layout types, like structs. So you can have pointer to structs, and it has meaningful data layout, which is the same as in C. We also have function pointers and a bunch of other things to basically make it easy to call C code. Generally, you don't have to use this kind of extensions at all. They're actually there only for Interup. Pointers are also extremely useful for kind of having a lower level GC-free subset of the language that you can use for extremely performance-sensitive applications. But again, you don't have to use any of this. So the core Scala is really as close as we can make it to be the same as in JVM.
Makes sense. And I guess with the pointers, then you can kind of approach that perfect GC we were talking about. So if you've added a concept like structs, like structured types and functional pointers, like doesn't that make it the language like a superset? Like are these new keywords in the language?
So
new syntax?
We don't add any new syntax whatsoever. So our rule is it should type check and without any problems, but by normal compiler. It might not make sense, but essentially all of our extensions are tied to like magical intrinsic methods or magical annotations, which modify how we compile things. But at the same time, they still type check one-to-one by Scala compiler without changes. So for example, from a types point of view, it's the same language. From a runtime semantics point of view, it's quite different, but types are still the same, for example.
That makes sense, yeah. I think that's a nice way to do it. So, I mean, because you're using annotations, does that mean that you can actually cross-compile? So the same source can be a native binary and a jar?
Absolutely. So we do support for cross-compilation. So cross-compilation is done through this SBT cross-project plugin. It's an SBT plugin that lets you cross-compile against three major targets, which is JavaScript, JVM, and native. These targets are basically treated as a separate sub-projects of one mega project, which is called cross-project. From SBT point of view, they're kind of like separate projects with separate jars, but we try to streamline end-user experience so that it really feels more like one single project, which you really just manage through this cross-project API. But overall, the idea for cross-compilation is you can create a cross-project with one or more platforms, and then when you compile and publish, you publish one jar per every platform you want to support.
How about libraries? Like the Scala standard library, I think is kind of very important and kind of gives the language a lot of its feel. So do you have the standard libraries available natively?
So standard library story is a bit involved, but generally the idea is Scala standard libraries are, and you can use it unchanged. Things like collections and standard types are there, and they just work. And the way it works is Scala library is implemented in terms of Java APIs very often. And instead of trying to rewrite the whole library and have like compatible but different library, we do a bit more involved thing, which gives us a better compatibility story, is we implement subsets of JDK APIs, which are used by Scala standard library and popular third-party projects to be able to have the same code on both JVM and native completely unchanged. Like, for example, projects like utest and fastparse, to cross-compile to native, they had zero changes in the source. They only had to change the build to support across projects, and that's it.
So what about the JDK? Like, I assume that's underpinning a lot of this Scala standard libraries, JDK calls.
Yeah, so basically, those are the Java libraries we care about. So in typically what it means is we have our own pure Scala implementation of JavaLang, JavaUtil, Java I/O, Java NIO, and a bunch of other things, which are essentially core APIs which people rely on in open source projects and in Scala library. We try to implement those as faithfully as possible to their reference implementation on the reference JVM, but we don't look at the source of the reference JVM because we try to kind of stay away from the GPL code as much as we can. And essentially, Scala is BSD 3 clause licensed, and our implementation is BSD 3 clause licensed. And one of the only inspiration for some of the parts of APIs we implemented was Apache Harmony project, which is a reimplementation of Oracle APIs without GPL, but under Apache license. So it's we sometimes use it for some cases where it's hard to reverse engineer the underlying behavior of the JVM, and we need some help there.
Interesting. I hadn't heard of that project. So if you're recreating the, I'm just thinking there could be the case where an implementation detail of some aspect of the JDK actually becomes something that becomes dependent on. And then when you have a new, native implementation and somehow that varies and things break, have you come across any cases like this?
We already experienced some of those. Technically, every time we see some of this, it's a bug in native, and we fix it as soon as we can. There are differences that we know of. Some of them are seemingly minor, but they can still cause accidental breakage. Like, for example, our float toString, like JavaLang float box type toString, has slightly different output format, which still outputs the same number, but has sometimes more trailing zeros than the one on JVM. And it has caused some open source test projects which rely on toString output to be exactly the same as in JVM to fail. We try to fix those as fast as possible, but for some of them it's a bit hard. But our philosophy is, if you can observe the difference from the reference implementation, it's a bug. And we have it either on issue tracker or fixed.
Indeed Prime flips the typical model of job search and makes it easy to apply to multiple jobs and get multiple offers. Indeed Prime simplifies your job search and helps you land that ideal software engineering position from companies like Facebook or Uber or Dropbox. Candidates get immediate exposure to top companies with just one simple application to Indeed Prime. And the companies on Prime's exclusive platform message the candidates with salary and equity up front. Indeed Prime is 100% free for candidates. There are no strings attached. Sign up now and help support Software Engineering Daily by going to Indeed.com/SEDaily. That's Indeed.com/SEDaily if you're looking for a job and want a simpler job search experience. You can also put money in your pocket by referring your friends and colleagues. Refer a software engineer to the platform and get $200 when they get contacted by a company, and $2,000 when they accept a job through Prime. You can learn more about this at indeed.com/prime/referral. That's indeed.com/prime/referral for the Indeed referral program. Thanks to Indeed for being a continued sponsor of Software Engineering Daily. If I ever leave the podcasting world and need to find a job once again, Indeed Prime will be my first stop.
Wow, that's a hard standard to hold yourselves to. I mean, to me, it almost seems like, their tests shouldn't be dependent on the number of zeros that a two-string implementation does.
Yeah, I know.
I'm interested to hear if any of the large Scala frameworks can run on native. I'm thinking like Spark or Akka. I don't even know, the Play framework. Has any large project been taken over?
So as far as I know, nothing major has happened yet. Probably the biggest code base that has been cross-compiled is Scala C, which has been done as part of our recent experiments. Technically, it's not hard to compile the source to NAR, like the first step. What's hard is to satisfy all of the Java dependencies, all of the Java library assumptions, which are expected by these projects. Like, for example, to run Akka, you need like good I/O support. Like, for example, to run Akka HTTP, you need complete socket support. Some of these parts are still work in progress. Like, for example, sockets has been just merged in initial support for sockets has been just merged in the previous release, and we're still working there. So it's a bit early for like major frameworks like Spark to just happen out of the box. But we are constantly looking at basically what's blocking people in terms of Java library coverage and in terms of APIs we support. And in fact, we're often implementing things just based on reports of people trying to port libraries. Typically right now it's smaller scale open source projects like UTest and FastParse. But still even for those to run cross-compile and test them, it often like all of the small differences in the library semantics are important.
So you mentioned Scala C, the compiler has been ported over. Could you describe like why and how that went?
So we had this like still private, kind of mostly private experiment to port the Scala compiler to the Scala Native. And the idea is right now on JVM, because of the startup issues, you kind of have to have SBT always in the background because otherwise compiler is just unusably slow. It's only usable after it's warmed up after a few compilations. But if you have native, we don't really have to have this problem because the very first run is already optimized. So you can already run optimized code immediately. And what we observed in our very early experiments right now is that we offer significantly faster performance on cold compilations. And on simple projects like understands line of code, it can be like times faster. So basically, cold build with Scala C on JVM can be like 2 to 3 times slower than cold build on native.
Wow, that's amazing. I mean, one of my frustrations with Scala is, the cold compilation time can be longer than any other language that I can think of. So what were some of the challenges of moving it to native?
So probably the major challenge was to have enough I/O. So we had a long story of doing file I/O and different types of file I/O because Scala C like uses almost every single type of file I/O JVM has. Don't ask me why, I don't know, but it basically uses NIO, it uses Java I/O, and a bunch of other things. So also things like jar and zip APIs. So most of those have been contributed by Martin Duhem from Scala Center. And it's been extremely helpful to make this even possible because essentially without these libraries a project depends on, it's hard to run it on native. So basically those are probably the hardest parts. We also have a work in progress port of Scala ASM. So Scala ASM is a fork of ASM library, which is a Java bytecode generation toolkit, which basically lets you programmatically emit Java bytecode. That's what Scala C does all the time. So we have a limited subset of that library ported to native to have enough APIs to make Scala C compile and emit class files. But otherwise, those basically were the only challenging parts. So we only the library problems, we haven't really discovered any major bugs in Scala Native this way. So as soon as we had enough Java libraries, it ran basically. That's basically it's a typical story of porting stuff to native.
Once those libraries are in place, then it works great. So if I'm in Scala Native and I have access to C as well as to, Scala and JDK libraries, like what is a string? When I create a string, is that a native string? Is that a Java string? Is it immutable?
So Scala string is an instance of type Java string, which is immutable string baked by a Scala array, which is also garbage collected, which is quite different from what C has for arrays, right? So C has just basically a sequence of bytes in memory, which end with trailing zero. This memory can be really anywhere because it's C and it's untyped and so on and so forth. So when you call an API which expects a C string, you need to convert Scala strings to C strings. In some cases where you have the same data representation in both Scala and C side, you can share data structures, but often you have to copy this data over if they're in completely different formats. Like for example, for file I/O, when you read or write bytes, we can just share memory with Scala Native arrays without copying. So it's not often the case that you have to copy data over.
So you can use either, and you get to choose, and there's some helpers for going back and forth.
Absolutely.
Yeah, I can see why that would be very useful. What hardware architectures, what platforms can Scala Native run on?
So technically, we have a very little requirements, but right now we only test on 64-bit architectures. Our CI, like all-time CI, is Mac and Linux 64-bit Intel. People have reported, and it seems to work on 64-bit ARM unchanged also. We don't officially support ARM at the moment, as in we don't have CI for it. But generally, just about any 64-bit architecture should just work out of the box. We only had reports about ARM and Intel, but maybe more obscure things like PowerPC would work too, but we don't know for sure because we don't have this kind of hardware. So basically anything with 64-bit pointers should just work.
I think now I kind of understand a lot of the usage around Scala Native. What interesting projects have you seen making use of this project?
So there have been a number of experiments going around. So one of the more interesting ones, there is this experimental framework in development called Dinosaur. And it's actually very, very early stages, but it tries to be like native first web framework, which currently is built on simple stuff like CGI. The authors experimenting with fast CGI now, and it seems like it's an interesting place to be because up until a point we have a stable web framework. Basically, the first framework to market will be the main framework for Scala Native probably. So it seems like Dinosaur has like the biggest lead to market so far. And there is already quite a bit of code working and quite a bit of experiments. And you can check one of the Richard's blog posts. I think we had some of them retweeted from Scala Native Twitter. But basically, the idea is to do a native first web framework, which is pretty cool. I've also seen people do different types of command line tools. And this is basically the area where we excel. And this is the area where JVM is often borderline unusable performance-wise.
Just because of the warm-up time, yeah, if you write a command line tool, it just is slow.
Yeah.
So because of that quick startup time, I'm interested if anybody has thought of, or if you think it'd be a good idea, to use Scala Native for things like Amazon Lambda, like serverless computing.
It's probably an interesting idea. I've never seen anyone try it on. It would be interesting to see how it works out.
I think I saw some talk on your website about compiling down to iOS, like to make an iPhone app. Is that a real thing, or?
So people tried compile to iOS, and it seems to work in principle. The main challenge with iOS is Interup with Objective-C. Right now, we don't support Objective-C, so it's basically you're a bit in an uncomfortable place. So right now, as far as I know, nobody's actively trying that. So it's possible in principle, but it's not directly on our shared list in terms of things we want to do now.
I think that you mentioned earlier that you were inspired by Swift with the LLVM intermediate language. Is that right?
Yeah.
So how did it inspire the implementation of Scala Native?
So Swift is cool and everything, but the major inspiration for Scala Native was Scala.js, because before Scala.js, it was basically considered like general truth that it's too hard to implement Scala outside JVM. So essentially, major inspiration for Scala Native is Scala.js and not Swift. So the way Swift influenced Scala Native is mostly in terms of compiler technology, in terms of what we do under the hood. So Swift has this intermediate language called SIL, which is short for Swift Intermediate Language. And it's kind of like higher level LLVM IR. And it's basically the area we're also aiming for with NIR, like higher level LLVM IR like thing. The main difference between SIL and NIR is that SIL is reference counted and NIR is garbage collected. And basically, that's probably the main major difference between the two. But otherwise, they're trying to solve a similar problem. Both are representation for high-level optimizing a compiler for high-level language. And they both try to optimize parts which LLVM cannot do well, because LLVM is actually a very low-level API and very low-level representation. Because, for example, some things are just simply gone by the time you emit LLVM IR. One of our long-standing issues is performance of virtual dispatch. We already did a lot to make it pretty fast, but still, an LLVM, when you compile virtual dispatch, you typically end up with calls through function pointers. Basically, this is what you compile down to. And when you're at that low level of abstraction, it's really hard to optimize this away. So LLVM typically does very little, close to nothing, to optimize virtual dispatch. So this is what we do ourselves. So SIL also solves a similar problem. It's a format for pre-optimization before LLVM optimization happens. So you try to make LLVM job as easy as possible and to emit high-quality code.
Was there any challenges with having a language that has two paradigms like Scala and kind of having this compile to LLVM?
Actually, I don't think this two-nature thing was a big problem. Probably the main reason is that essentially Scala compiler already does a functional to object-oriented part of compilation. Essentially, all of the high-level functional features are replaced by equivalent object-oriented features. So typically what you end up by the end of the Scala compiler is very object-oriented code. And essentially, most of our challenges to make functional code work well are the same as to make object-oriented code well. Because in the end of the day, for example, closures are just object with virtual methods, just the same as any other object-oriented thing. So basically, it all compiles down to the same representation where it has the same format for both object-oriented and functional features.
That makes sense, yeah. So that kind of part is taken care of for you. What features are up and coming in Scala Native?
So right now, we are pretty much complete in terms of language support. So we don't know of any major semantic difference, which will be a breaking change, as in we would like to fix it as soon as possible. And most of the innovation right now is happening in libraries. So we are slowly working towards bigger and bigger coverage of our implementation of Java APIs. One of the major things which we're trying right now are multi-threading APIs, like, for example, things like locks, concurrent atomic primitives, and so on and so forth. And apart from that, also networking and things like that. So basically, those are typical APIs you would need for a backend microservice kind of app. This is kind of the area which we see Scala Native being used more in the future. So apart from library innovation, we do lots of work on the compiler code quality and the runtime code quality. So basically, those are small iterative changes of the common patterns we see, basically to improve performance, to reduce overhead, to reduce a footprint, to make it even more lightweight, and so on and so forth. I guess that's pretty much what it is. One of the areas where probably see the biggest changes, which are like non-iterative, incremental, slow convergence towards better performance, are changes to the garbage collector. It's probably the area where we could do things significantly better than what we do now.
So if people would like to learn more about Scala Native, where should they go?
The standard place is our website, scala-native.org, and our Twitter, twitter.com/scala_native. Those are the two central places for announcements, latest releases, and so on and so forth. You can also go to Gitter, and so Gitter is like a nice, cozy chat room for like if you just try and Scala Native, something doesn't work or you have a problem. It's basically a place where you go to ask questions. And of course, for all of the active development, we use GitHub and GitHub issues like pull requests and discussion on what's going on is happening over there. So basically, if you subscribe to Twitter and Gitter and GitHub, that's pretty much you will see everything that's going on.
And I understand since you first announced this project, you've had a lot of contributors. Is there a lot of contributions coming in?
There's actually quite a bit of contributions. Right now we have a bit more than 60 contributors overall. It's really nice because people often contribute sometimes small things, sometimes bigger things, but it's really, really nice to see people interested in the project and trying to help as much as they can.
Yeah, that's great. It's great to have a community involvement, that it's not just a couple people working away on it. Well, thank you so much for your time, Dennis. It's been great to learn about Scala Native.
Thank you for having me.
Thanks to Symphono for sponsoring Software Engineering Daily. Symphono is a custom engineering shop where senior engineers tackle big tech challenges while learning from each other. Check it out at symphono.com/sedaily. That's symphono.com/sedaily. Thanks to Symphono for being a sponsor of Software Engineering Daily for almost a year now. Your continued support allows us to deliver content to the listeners on a regular basis.
Wow!